In this video I'm going to make measurements on hybrid couplers, that is hybrid splitter combiners. I will measure them as splitters because that's how I'm going to use them later on in measurements. I have two strong signals, one on 12 MHz, another one close to 13 MHz. They are both amplified by 6 dB, and then they go into a combiner, something from mini circuits that is by far free of intermodulation. Then the signal goes through this box, which is a notch filter, but it is also a nice low-pass filter up to 17 MHz. The purpose of this is to guarantee that the overtones from the signal generators do not reach the test object, because mixing with an overtone, that is second order intermodulation, and that doesn't go to zero as quickly as the third order does. The two signals, the two tones, go through this attenuator, which right now is set to 0 dB. Then they pass through this box, which is a notch filter on 13.998 MHz. After that there is a 6 dB attenuator. It is carefully selected for low intermodulation. Then the signal goes to this directional coupler that can inject a 20 dB suppressed signal. The test object is inserted between this directional coupler and the receiver here. So here is the receiver. It starts with a carefully selected 6 dB attenuator. Then comes a bandpass filter, and after that a low noise amplifier and a persives. The purpose of the bandpass filter is to protect the persives and the low noise amplifier from the strong signals. The attenuator is here to guarantee that the test object is looking into approximately 50 ohms on all frequencies. This filter has very high standing wave ratio at the stop band, that is 12 and 13 MHz. And this attenuator is to make sure that the test object looks into 50 ohms at the frequency of the notch. And the test object will be inserted in this wire, going from the directional coupler to the receiver. This is the receiver input. I have connected this generator to the receiver input, that means the attenuator, and place the signal in the filter of Linrod, a fairly narrow filter, and I've calibrated it to show -100 dBm. So now the level is calibrated on the attenuator input, and you can see here the filter bandwidth is about 50 Hz. That's in which bandwidth I'm looking for the intermodulation, and also for this pilot tone that I'm using for measuring the loss through the test object. I have now reduced this level by 20 dB and connected the cable to the directional coupler. And I should expect to see still -100 dBm here, because the coupling in the coupler is 20 dB. And indeed I do. The strong signals are present, and you can see the intermodulation between them here. I click on it to bring it to the center of the filter, and you can see the level of the intermodulation product is in the order of -130 dBm. It's close to the noise floor. I place the mouse on the signal here and attenuate the two strong signals by 1 dB. One more dB. 1 more dB, 1 more, and it looks at least close to third order. Inside this box there is one of these, a PSCQ214 with data, as you can see here. It is not symmetric, so I look first in one of the ports and I see the intermodulation level at minus 74.5 dBm. And I click on the pilot tone, it's this one. Sorry, it's this one. And I can see how far it is from 100 dBm to get the loss through this device. And it's 3.4 dB. And now I look at the other port, and there the loss is 2.9 dB. And the intermodulation is minus 70.8. So this is the worst port, the one with the lower loss. Here are the results. Measured levels, loss. That means that the IM3 referenced to the input is minus 67.9, and from that I can compute the intercept point at the input as plus 47.5 dBm. And that means at the output I have plus 44.5 dBm. If I would connect an IC7800 after here, having an input intercept point of about 40 dBm, that means that the tone generated by the splitter hybrid would be 60% of the intermodulation generated by the radio. And those signals could add to form a 1.6 amplitude, or they could subtract to form a 0.4 amplitude. So it's a very large error from 0.4 to 1.6 in voltage. It's a factor of 4, means 12 decibels. That's the range that the result could be uncertain within, plus minus 6 dB. So this combiner splitter isn't good enough for measuring the best radius we have in the ham market today. Inside this box there is one of these, a 3-way splitter combiner. The intermodulation level is very similar in the 3 output ports. It goes from 112.9 to 113.5. So I say 113 for all 3. And the attenuation through the unit is the same in all the ports also. The loss I find is 5.2 dB. This unit looks good. The output IP3 is plus 62 dBm. So I think it is well above anything that I can come across on the amateur market. This is an iron-free combiner. It has a coil that is tuned to 14 megahertz to provide opposite phase, and then a resistor across to load, and then a pi filter to match from 25 to 50 ohms. So there are some components in there. The loss is 3.2 dB, and it doesn't give any intermodulation. This hybrid is made with these cores with copper to prevent any magnetic field from leaking out in the air. It is also free of intermodulation, regardless how the wires and dummy loads are connected. As you can see here, very low intermodulation. And I turn the level down. Three dB, and no surprises. This hybrid is made with these binocular ferrites. It is not very good. As you can see here, connected different ports, but the worst one is minus 67 dBm. So this is not very useful. Finally, I verify the two strong signals. This is the signal that normally goes into the test object, and as you can see, plus 9 dBm. And it's the same for both signals. Now, after this section, I will show some clips I made on the way to reach this setup. There were problems with intermodulation at various places that I had to eliminate. And I will show the numbers that are shown are less accurate because they are impaired by the various problems that were gradually found, as you can see. This is an homemade hybrid. It uses two of these ferrite cores. The intermodulation is fairly high. I can read minus 67.7. And I can check what happens when I go down in steps of 10 dB. 10 dB, pretty accurately from, 65 to 90. 10 more dB, from 90 to 120. That is 30 dB. And one more. Now we are at the noise floor. And I check the test signal to see how far from minus 100 it is, because that gives us the attenuation through this hybrid. 3.5 dB. This is another hybrid. It has the same schematic diagram. A transformer with the center connection where the signal is fed into this transformer. The outputs, two of them, and then there is 100 ohms from here to here in the form of a step up by a factor of 2 transformer here, impedance wise, and this is one of the inputs. And the other inputs is here, and it is stepped down from 50 ohms to 25 ohms. It is done with this kind of ferrites, and the ferrites are wound with more turns to load the ferrite less and to make it work on higher frequencies. Despite that, the holes are filled with copper, as you perhaps can see here, or maybe better here. That is to prevent the magnetic flux from going in the air in the hole. I want to force it into the ferrite. And I also wrapped copper foil around the outside to not allow any leakage in the air from the wires that go on the outside to form closed turns. The intermodulation from this combiner is so small I cannot see it. If I look for the level, it's minus 130. This is a stepped attenuator. It is set to 0 dB. It gives a significant amount of intermodulation, minus 71 dBm. The reference signal is minus 100.6, so the attenuation is 0.6 dB only. I have activated each one of the switches 10 times. The attenuation is now 0.3 dB only, and the intermodulation is at minus 109.5. I have now activated each switch 15 more times, and the intermodulation is now down at minus 136. It means it cancels to some extent the intermodulation of the measurement system. And I look at the attenuation. And you will see here minus 100.25. So loss is 0.25 dB now. The background signal on the IM3 frequency varies with time. And you can see that here this doesn't look like normal white noise. Not for a signal that is strong like this. And it's particularly visible in the waterfall. I don't know the reason for this, but I will do some investigations. I have cleaned all connectors in isopropanol, and now things look much better. You can see the level in the waterfall, it's constant now. If I reduce by 3 dB, you can see the signal here. Well, I go back, it's now 26 or something. And it goes up to 35. I expect 12 dB for third order, and it's not far from that. I think before there was intermodulation from several different places, which was a little bit random because it was because of bad contact. So these different intermodulation could add or subtract to produce a very unstable situation. But that's not the case now. The output attenuator is critical. Here I have one which is identical, and I replace it. And it's clear this one has a very large third order intermodulation. You can see here. Now this second one, I didn't clean the two adapters. I will do that. I have now cleaned these two adapters, and as we can see here, it didn't make any difference. It's the attenuator that is causing intermodulation. Now I put back the one I started with. I labeled it minus 132, because when I read here, what I see is minus 132. Here is an attenuator with TNC connectors, and the level I find is minus 129.6, let's say 130. Metal film resistors, 0.25 watts, are not particularly good. The intermodulation level, as you can see here, is minus 125 dBm. I have measured many 6 dB attenuators. This turns out to be the best one. And here is the collection. These two. The IM3 level from that stepped attenuator is minus 133 dBm. These two look identical, but they are not. The one on the left hand side is at minus 132 dBm in intermodulation, very close to the best, which was the stepped one. The other one is at minus 67. That is a very high level of intermodulation. I would regard it as defective. The manufacturer is JFW. These ones are also from JFW, TNC connectors. They are all very similar, between 129 and 130 dBm is the level for the intermodulation. These are from mini circuits. They are all identical at minus 102 dBm. That is 30 dB more intermodulation than what I see in the best attenuators. These two are also from mini circuits, 6 dB with BNC connectors, 120 and 115 respectively. This one, for microwaves up to 18 GHz, gives minus 125, while these two series connected 3 dB give, minus 52, which is a very strong intermodulation signal. So this is useless for the purpose of intermodulation on HF. And finally, these stepped attenuators are at minus 120 and 125 respectively when set to 6 dB. There can also be problems with bad cables. And here is one. And I look at the screen to see what is the intermodulation level. Minus 118. So this is clearly not good. What I need to do is to tighten the nut here on the BNC connector. Here. About half a turn. And that brings the intermodulation down to the normal level of the system. So now I'm going through all my cables to see which ones are bad.